What does the sun sound like? At first the answer seems obvious. The sun is silent, of course. Space is a vacuum and sound cannot travel without a medium. To us, our star has always been mute. But let's push aside that simple answer for a moment. What if in some imaginary scenario sound could travel through space? What would it be like to live beneath a sky where the sun's voice could reach us? Would we hear a gentle song, a cosmic melody soothing us each day? Or would it be an overwhelming roar so powerful it might be the last thing humanity ever heard? Strangely enough, scientists have been able to get close to answering this question. Using spacecraft such as the Parker Solar Probe, which currently skims the outer reaches of the sun, they detect pressure waves, plasma oscillations and magnetic disturbances. These signals can be converted into sounds our ears might recognise if space allowed them to propagate. And these sounds are not only fascinating to hear, they also carry clues to some of the greatest mysteries of our star. So let's listen together. Imagine for a moment that space suddenly gained the ability to transmit sound. From our home here on Earth, 151 million kilometres away, the sun would not be silent at all. Instead, we would hear a deep, unrelenting hum echoing across the void. The sound would resemble a steady electrical buzz, like the vibration of countless generators running at once, or the faintly menacing aura of something radioactive. Which in a way makes sense because the sun is a giant nuclear reactor. Every second it releases about 3.85 times 10 to the power of 26 watts of energy. That's roughly 1,000,000 times more than all of humanity produces in an entire year. Now, what would that much energy mean for volume? Let's picture it. Take whatever device you're watching this video on, connect it to the loudspeakers of a rock concert, and then play the sound at full blast, at around 110 decibels. That's the volume level scientists estimate the sun would have here on Earth. Survive it for a few minutes perhaps, but eventually the entire human population would be deaf without ear protection. And remember, this isn't occasional. It would be constant every hour of every day forever. We should consider ourselves lucky. Evolution may have shaped us without hearing altogether if such noise really filled our skies. Because the closer we travel toward the sun, the more unbearable it becomes. Near its surface, the sound might reach an astonishing 270 decibels. To put that in perspective, Earth's atmosphere physically cannot carry sounds louder than about 190 decibels. The sun would be producing vibrations 100 million times stronger than that limit. So while the sound from Earth would already be deafening, moving closer would immerse us in a violence of noise no living creature could withstand. And yet hidden within those overwhelming layers of sound are subtle details. To understand them, we need to venture nearer. As we approach, the uniform buzzing gives way to something more complex. The next sound we encounter is the solar wind. The sun constantly blasts streams of charged particles across the solar system, and if space could carry sound, we would hear it as a restless shifting murmur. But here lies one of the sun's great puzzles. Where does this relentless wind gain its force? Intuitively, one might imagine particles bursting straight from the sun's surface, driven outward by nuclear fusion's energy. Yet observations from the 1960s showed something strange. Particles inside the sun's outer atmosphere, the corona, were moving relatively slowly, only about 145 meters per second. But once beyond the corona, those same particles were suddenly accelerating to 618 meters per second, transitioning from subsonic to supersonic speeds. Something in the corona was propelling them forward, almost like a hidden engine flinging material into the solar system. And the mysteries do not end there. Consider temperature. We expect heat to be greatest at the sun's core, gradually cooling as we move outward. But as soon as we reach the corona, the pattern breaks. The surface of the sun simmers at around 5,600 degrees Celsius. Yet only a short distance above the corona suddenly blazes at more than 2 million degrees. Instead of cooling, the atmosphere grows unimaginably hotter. Why, what invisible process is heating the sun's atmosphere and accelerating its winds? To uncover clues, we must listen more closely. Crossing into the boundary between the corona and interplanetary space called the Alphen surface, another sound emerges, Langmuir waves. These are created by plasma particles vibrating as they interact with streams of light and magnetic funnels rising from the sun's surface. The sound they create is eerie, like a kettle beginning to boil, a bubbling hiss echoing from oceans of plasma. All across the sun's surface, giant islands of hot material rise, cool, and sink again. As they churn, they drag magnetic field lines with them, stretching and twisting invisible threads. Plasma becomes trapped, then funneled outward, beginning the long journey into space as part of the solar wind. The exact mechanism remains a mystery, but listening to Langmuir waves gives us a glimpse of the processes at work. They are both hauntingly beautiful and scientifically invaluable. As the solar wind streams outward, not all waves travel at the same speed. Faster ripples surge ahead, while slower ones lag behind. The result is dispersive waves filled with delicate chirps, little bursts of sound where quick waves collide with slower ones. Over distance, these differences smooth out. The chirps fade and the sound becomes the steady buzz we first imagined from Earth. But before it blends away, those brief scattered notes tell us about the sun's restless and uneven heartbeat. Yet perhaps the most dramatic sound comes when we enter deep into the corona again. Here we begin to detect what are called Whistler mode waves. On Earth, these waves occur too usually as faint echoes after lightning. A storm may flash and thunder, but it also sends ripples through our planet's magnetosphere. With the right instruments, they appear as small whistles, fleeting and quiet. On the Sun, however, the difference is staggering. Instead of an occasional whistle, the corona produces a continuous storm. The sound is no longer scattered or subtle. It becomes a cacophony of wailing and roaring, as though the entire star is endlessly cracking with invisible lightning. And behind this immense roar lies one of the leading explanations for the sun's two great mysteries: why the corona is so hot and why the solar wind accelerates so violently. The phenomenon is called magnetic reconnection. The sun is a seething ball of plasma wrapped in tangled magnetic field lines. As hot material rises and falls, these fields twist, bend, and loop, forming the iconic arcs often seen in solar images. But when two field lines meet, tension builds to a breaking point. When they snap into a new configuration, an enormous release of energy occurs. It's as though two colossal rubber bands stretched to their limits suddenly collide and recoil. The result is explosive arcs of magnetic force fling outward, carrying plasma into space at extraordinary speeds. These violent events are called nanoflares. Though small compared to the scale of the sun, nanoflares are still unimaginably powerful. Each one can heat nearby plasma to millions of degrees in an instant. Scientists believe that countless nanoflares happening all across the corona could together explain both its blistering temperatures and the constant outflow of solar wind. This is still a developing theory. Nanoflares are only recently detectable with advanced instruments, and researchers are still debating whether what they observe matches the long-predicted phenomenon. Yet the evidence is compelling, and the sound of the Whistler waves roaring endlessly may be the voice of these hidden explosions. The mysteries of the sun are far from solved, but every orbit of the Parker Solar Probe brings us closer. This spacecraft, now only a few years into its mission, continues to gather wave patterns, magnetic data, and particle measurements, transforming invisible processes into sounds we can interpret. It's almost poetic. Just as we can listen to the ticking of a clock to deduce the mechanism inside, so too might we one day understand the workings of our star, not only by what we see, but by what we hear. The sun is not silent. It hums, it hisses, it roars, Its voice tells stories of fusion and fire, of winds and storms, of tangled magnetic fields that snap with the force of a million bombs. And though we cannot hear it directly, science gives us the chance to imagine, to translate those invisible rhythms into echoes we can comprehend as we continue to explore who knows what other sounds the universe might reveal. The whispers of distant planets, the pulses of neutron stars, the rumbles of black holes, each a clue to how the cosmos works. So the next time you look up at the sun, remember, if the universe had sound, you would be standing under a constant thunderous symphony, a reminder that even in silence, the cosmos is never still.